Hi, everybody. In this video, I'm going to go through lesson 3.3, which is styles of proofs. So first, I want to talk about what is a two-column proof. And this honestly is kind of like our most basic proof. And it is a table. Oh, the table of statements with supporting reasons. So if I have a two-column proof, we are usually given something and we want to end up proving something else. So I'm going to set up this table and it has two columns, hence the name two-column proof. And on the left, that is your statement or your argument, if you will, that you are using to get to your proof. So you will start with your given statement. So you'll list just whatever is given. And your reason, your supporting reason is because it's given. And then you will go throughout your proof using logic and reasoning, using properties you know. So deductive reasoning. You could use a little bit of inductive reasoning too here. Every once in a while, you may. But for the most part, it's going to be deductive reasoning, more reasoning, using things that you know to arrive at your end conclusion. Then you will get to your end. So two-column proof, this is our most basic proof. We also have a paragraph proof. And you could turn a two-column proof into a paragraph proof. A paragraph proof, the main difference is that it uses complete sentences. And it's kind of, if you think about it in an essay, it's kind of like the conclusion paragraph of your essay. You're summing it all up. You're putting all of the pieces together. You're including what you need using those complete sentences. So we have paragraph proofs. We also have flowchart proofs. And a flowchart proof, I meant to underline paragraph proof. A flowchart proof is definitely the more visual option. So maybe make a note. More visual. And the reason it's more visual, you can see the structure. You can see the logical structure. How did we get from beginning to end? And how does it all fit together? So your flowchart proof, oops, each, oops, each given piece, you always start out with those pieces of given information. Each given piece is in its own box. Gets its own box to start out. So you have these boxes along the top with your given statements. And then you will start to use those supporting reasons to make statements. So you'll have supporting reasons and statements connected with arrows. So I think it's better to see it. So maybe we have some given statement and I'm able to use some property we know to make a statement and give the reason. And maybe I use the other given statement. There are two given statements. And I'm going to have some statement, something I'm going to be able to deduce. And then maybe from there, I'm able to kind of draw these two separate statements together. So now I have a new statement maybe that I can form with these two together and some supporting reason. So I'm using reasoning and I'm making my arguments. This is kind of like the body of our proof here. And then we get to the end. We reach our final conjecture. So the conclusion or the conjecture, let's see, I'm going to do it in blue. So the conjecture, the conclusion, the end of the proof is at the bottom. So using our reasoning, using what we know about the problem, we are able to arrive at our final conclusion. And this really, no, this is what we were trying to prove. So maybe I'm going to say instead the goal of the proof. This conclusion was the goal of the proof. So this, I love this structure because you can really see what's happening, but you could always take what's happening and write it using words and sentences. Okay, I want to now talk about algebraic proofs. And algebraic proofs can be made in one of the styles. I could do an algebraic proof using a two-column structure, using a paragraph style, using the flowchart proof. So algebraic proofs really and I should have been writing that, you could use the two-column structure. You could use a flowchart. You could even use a paragraph proof. So all of these to prove some statement. A lot of times your algebraic proof, your goal is to prove maybe you're trying to prove that x plus 3y minus 4 equals 10 if and only if some other statement is true. That's just one example. But we have lots of different properties that we will use and refer back to whenever we are dealing with something that is algebraic in nature. So we need to define these kind of basic properties of equality. Most of our algebraic proofs, again, are involving equations. So basic properties, of equality. Okay, so there are three, oh, well, not quite what I was going for. So let's just, sure, that works. There are three basic properties of equality. The first is the reflexive property of equality. And the reflexive property of equality is very straightforward. If we have A equals A, then we know that A is equal to A, straight up. Number 1 is equal to 1. 2 is equal to 2. 2x is equal to 2x, right? Any term, any object is equal to itself. This will come in handy. It will. We will use this. Next, we have the symmetric property of equality. I'm just going to call it the symmetric property. And the symmetric property states if some object A is equal to B, then we know that B is equal to A. So for example, if x equals 10, then 10 equals x. You can flip it, right? It's symmetrical. And lastly, we have transitive property of equality. And the transitive property is my personal favorite. It states if A is equal to B, and we also know that B is equal to C, then we can conclude that A has to be equal to C. So if I know object A is equal to object B, and object B is equal to object C, then altogether I know A is equal to C. So an example of this, if X is equal to Y and Y is equal to 3, then we know since X is equal to Y and Y is 3, X also is equal to 3. That's using the transitive property of equality. So those are our very, very basic properties of equality. We also have some algebraic properties of equality. And these are all super important to write down because we're going to use these all throughout our Algebra 1. Nope, this is geometry, all throughout our geometry journey. So please make sure you are writing these down. I said Algebra 1 probably because I was writing algebraic. So we use these a lot in Algebra 1, actually. The first one is the addition property of equality. I'm only going to make us write property of equality once. So the addition property of equality, that's its full name, so we should really call it by that. The addition property of equality says, and by the way, for all of these examples, we are assuming or we're given if A is equal to B. So if I have two objects A and B and they are equal, the addition property says if I have A and I add on some term C, this is equal to B plus C. What I add to one side, I also add to the other. Next, we have the subtraction property of equality. I'm just gonna, I don't want to call it just subtraction property, because now we are really dealing with an equation. So property of equality. If, oh, I lost my C. If I have some term A again, and that is equal to B, and I take A and subtract C from it, that is the same thing as taking B and subtracting C from it. If I subtract from one side, I also subtract from the other. The multiplication property of equality states that if I have that term A and I multiply it by some number C or by some value C, that is the same thing as taking B and multiplying it by some value C. What we multiply to each side or what we multiply to one side, we must multiply to the other. And then we have the division property of equality. I don't love that Q that I wrote last time. The division property says if I have that value A and I divide it by C, that is the same thing as taking B and dividing it by C. And we again learned all of this last year. We just never formally wrote out these properties. Another property and the last property that we are going to define, and one that we will use a lot, is the substitution property. So, very basic example. If we know A is equal to 3 and B is equal to 2 times A, or 2A, we can evaluate, or we can simply substitute the value of A in for A. I'm going to substitute in 3 for A, so I have 2 times 3 now instead of 2 times A, and that is also equal to B. So B is equal to 2 times A. Since A is also 3, B is equal to 2 times 3. So now I can just multiply, and 2 times 3 gives us 6. So if A is equal to 3 and B is equal to 2 times A, then B is equal to 2 times 3, or 6. Alrighty, yes, you needed to write all of this down. So if you did not write down all of these wonderful notes, I'm so serious you need these, and we will use these throughout the year. And there are not examples that I'm going to go through in this video. I want you to now head to section 2, the learn, and then the guided practice. I want you to spend some time looking at the examples in the guided practice. Please let me know what questions you have, and I look forward to seeing you in class.